So now that we've formed our enolate ion with a suitably strong base, let's talk about how an enolate ion is reactive. It has two resonance structures, right? So the actual structure bears partial negative charge on both the oxygen and the carbon. As to whether in the actual structure, which is the major resonance structure, it appears that the oxygen has a little more partial negative charge on it, and that makes sense because oxygen is a little more electronegative. But that does not necessarily determine exactly where reaction will take place in this enolate ion. And it turns out that most commonly it's when the carbon reacts. Okay? It's because reaction at the carbon, it makes the more stable compound. So let's look at our options here. Right, two resonance structures of the enolate, the O minus and the C minus. If we were to have the O minus attack an electrophile, we get this enol ether, right? They call it an enol derivative. If reaction happens at the carbon, we end up with an alpha substituted carbonyl compound. So it turns out that the final stabilities of these two products are quite different. So as long as we're under thermodynamic control, the more stable product will predominate. So the CO double bond is more stable than a CC double bond. So the more stable product here will be formed as a majority. So in general, that means that in an enolate ion, the carbon is the more nucleophilic atom. Now, we can still use either enolate resonance structure to indicate that. Here is the carbanion resonance structure. Here is the O minus resonance structure. Both of these can attack an electrophile, and it's actually the same thing. So you can feel free to use whichever you want. On an exam, if you're told specifically to show both enolate resonance structures, you may have to show both of these, but otherwise you can choose whichever one you like. They can both equally attack an electrophile and get the same product. The carbanion resonance structure is probably more simple because you just have a C minus that attacks an electrophile, and that's easy. If you have the O minus resonance structure, what you can do is have the O minus come back down to reform the double bond, and then have the double bond electrons attacking the electrophile. And if you want to do it like our Pogel book, you can bounce it off the carbon there, just to show which carbon is forming the bond. Okay? Both are equivalent in their correctness, I guess, and in the product that's formed. Okay? So remember, both are correct resonance structures, both are correct ways of showing an enolate attacking an electrophile. What our textbook uses most often is the carbanion resonance structure, just because it's the easiest to follow. It's most consistent with the product that's formed.